In our last few lectures, we derived these equations. This one was familiar from our basic dynamics, the sum of the forces as mass times acceleration of the center of gravity. And we showed that this is true even for a collection of particles, as long as we talk about the center of gravity of that set of particles, or an elastic body, or a variety of things. We also derived a similar equation for the sum of the moments. And there, we had to be a little more restrictive. We found this equation that had a similar form, only we have this extra term where we have the mass of the system, a vector to point A from the center of gravity, or center of mass. And so we said that in a special case, we can make this look like the simple equation from dynamics. And the simplest and most common is where point A is the center of mass, or in other words, the sum of the moments about the center of mass is equal to the derivative of angular momentum about the center of mass. So that's one that we'll use a lot. Another special case is where point A is fixed, so that this acceleration goes to 0. So if we have a body that's pinned at a point, we'll sometimes use that special case. And then this last one, a somewhat esoteric case, where if the acceleration of A happens to be parallel to RGA, then the cross product between those is 0. That one's not super useful, but we state it to be complete. Okay, so in any of those cases, our two equations governing dynamics are sum of the forces, mass times acceleration, and sum of the moments is equal to the derivative of angular momentum. And we also talked about the fact that angular momentum is the product of an inertia matrix and the angular velocity vector, or angular velocity of the body. So we're going to need to review some things about inertia and cover some things about inertia to be able to make use of this. And then we'll talk about how we can take the derivative of this equation. All right, so inertia properties in general, the inertia is inertia matrix is a 3x3 matrix. The elements in that matrix are given by these integrals over the volume. So, for example, the inertia about the x-axis is an integral of the y and z coordinates. So the two coordinates perpendicular to that axis times each element of mass in the body. We add up all the mass. We're basically taking the squared distance from the axis to each piece of mass in the body. So we can do some simple examples here that will help us to make sense of this. Let's look at two examples quickly. So first of all, a ring. A ring is one of the simplest cases. So if we have a ring of radius r and mass m, for a ring, all of the mass is at a radius r. So if we have this integral, let's write it this way. Let's say we have x and y coordinates, and we're interested in the inertia about the z-axis, which is the double integral of x squared plus y squared dm. And if we look at this, in this case, that integral just becomes, that should be the triple integral, the integral of x squared plus y squared is just the radius squared. And the radius is a constant, so we can pull that out. So it's just the integral over the volume of dm, or in other words, it's just the mass times r squared. So in the case of a ring, the inertia is just mass times radius squared. And this is what gives us our physical intuition about inertia. Inertia is a mass, inertia about an axis is a product of the mass and the radius squared to where that mass is located. All right, let's do a second example. Let's say we have a long, slender rod, and we've got a z-axis here, a y-axis here, so x is along the length of the rod. And let's suppose that we want to calculate Iyy, which is the integral of x squared plus z squared dn. All right. So if this rod is long and slender, what we will say is we'll say that the z-coordinate and the y-coordinate of every point is approximately 0. So our equation there for Iyy becomes the integral of just x squared dn. And now we can work that out in a little more detail. We also don't need to integrate over y and z because they have 0 extent. So basically we just need to integrate x squared times dn. And what's dn? Well, we can say that dn is the total mass divided by the length times dx. So if we take a little piece out here that has a length dx, its mass, dm, would just be m over L times dx. Okay, so now we can evaluate this integral. M over L are constants, x squared dx, and we can integrate from minus L over 2 to L over 2. And so this will become m over L x cubed over 3 evaluated from minus L over 2 to L over 2. All right, so simplifying a little more, we have m over 3L and then x cubed, so this first one will be L cubed over 8 minus a negative, so that becomes plus L, oops, that should be a cubed, L cubed over 8. So we have 1/8 plus 1/8, which is 1/4. So this becomes m over 12L times L cubed, or 1/12 ml cubed. Oh, sorry, ml squared. All right, so what does this tell us? This tells us if we have a rod, if we kind of look at an analogy with the previous case, where we said inertia, so this is inertia yy, where we said inertia was like mass times radius squared. This tells us that our effective radius for this rod is L over the square root of 12. Right? Or it tells us that this rod is kind of like having a ring of mass that's in here at a distance L over square root of 12. Right? Its radius is here. So, so that's kind of the average effect of having some of the mass in the center where it doesn't spin at all and some of it out even farther. All right. So that's inertia. There's our example there. Products of inertia are a little harder to have intuition on. But if you look at the integral equation for them, for example here, these integral equations, they're basically giving a measure of asymmetry. So the nice thing about these is if we have a plane of symmetry in our body, then any products of inertia that are perpendicular to that plane become zero. So more specifically, if xz was a plane of symmetry, so this plane right here, then any products of inertia that include y will be zero. So ixy, iyx, izy, izx, iyz. So, and we can also show that if the body has two planes of symmetry, then all the products of inertia go away. So let's look at some examples. In the appendix of the textbook, you can see the inertia properties for some bodies. Here's the rod that we just did. So you don't need to derive that every time. You could just look it up. And we derived Iyy. Also, that's equal to Izz, and we say that the inertia about the x-axis is zero, or it's negligible. If we expand that rod to a cylinder so that this radius is non-zero, it's a little different because now the x-axis is this way, but now Izz is 1/2 mr squared. So that's our inertia for a disk. And the inertia about the x and y axis, the perpendicular, has that 1/12 ml squared, but then we also have this factor. All right, so neither of these have any products of inertia. They both have two planes of symmetry, so all of the products of inertia are zero. Here are some examples, other examples. So this cone also has two planes of symmetry, right? In this case, it'd be the xy plane and the xz plane. So again, no products of inertia, but this body right here only has one plane of symmetry, right? The yz plane, at least using the coordinate axes that we've drawn. And so this one does have non-zero products of inertia. Right? Now we'll go through a derivation that will show that, but we can even see that in the picture here. If we'd actually chosen our axes differently, so that we had an axis here, right? So say this was y and z. Hopefully you can see that in the 3D perspective. We'd still have the yz plane as a plane of symmetry. But then we could also have the xy, if we split this exactly in half, right? We could have the xy prime become a plane of symmetry. And then about those axes, these would all be zero. So, okay, so there's an example of how this can be done. We'll talk about that in a little more detail in a second. Here's just an example of one application of this from my research. This was some work we did quite a few years ago on an instrument called atomic force microscope. And the basic idea behind this instrument is that we have a cantilever beam with a sharp tip on it, and there are a few different modes of operation, but one of them is where you press the tip into a sample and you drag it along a sample, and you record the deflection of the tip to measure the height, the topography of the sample. You can also measure friction force and other things. And often an important question in all of that is, how hard am I pushing on the sample? I can measure deflection, so if I could estimate the stiffness of the cantilever beam, I could figure out what force I'm exerting for a given deflection. So what's typically done is they would treat the cantilever beam as a vibrating Euler-Bernoulli beam, and you can then derive what the natural frequency of vibration is as a function of the thickness and width and Young's modulus and things of the cantilever. So there are methods where that's derived, and all of those methods, it turned out, would ignore the mass of the tip here on the end. And you can see in this picture that mass can be fairly substantial. So one of my undergrad research assistants actually tackled this. We took some scanning electron microscope images of these cantilevers. We estimated the inertia of this tip. It's kind of like a cone with a piece missing. So we can use some of these ideas to calculate the inertia. And we put that into different models and saw what would happen to the results, to these calibration methods, if the tip mass was non-negligible. So anyway, there's just one little application of that. So a couple of things we might need doing work like that, right? If you look up the inertia properties for a cone, let's see, we just had them right here, right? It gives you the inertia about the center of, well, actually it looks like it's giving you the inertia about the tip here. Say you want the inertia about the base, right? Or about the center of mass. Actually, I think these should be the inertia about the center of mass. Anyway, if we are given the inertia about one point and we want, say, the inertia about the base, we can use the parallel axis theorem, which to apply this, we always have to start or end at the center of mass, or center of gravity. So suppose we had the inertia properties about little x, y, z, and we want them about x prime, y prime, z prime. We can define a position vector that goes from G to B, right? This position vector right here. And the parallel axis theorem tells us that the inertia about the new axes is the inertia about the original axes plus these translation terms. And those translation terms are just mr squared factors. Similarly, we can derive correction terms for the products of inertia. And these are actually really important to keep in mind because we can sometimes start with a body that has no products of inertia, and after going through the parallel axis theorem, we can end up with something where the products of inertia are non-zero. Okay, let's flip back to our rod and let's just try this again. So we derived the moment of inertia for this rod about its center, which happens to be the center of gravity. I guess we'll do a capital G. All right, so we derived that. What if we wanted the inertia about the end? So Iyy about the end, or if we match the notation that we just had, we'd have y prime, z prime, x prime. So I, y prime, that's going to be Iyy plus, we can flip back and just see to make sure we're getting this right, Iyy will need x and z squared times the mass. So we take the mass times xb squared plus zb squared. So these are the coordinates of point B, our new origin, relative to z. So this becomes Iyy about the center of gravity plus the mass times xb. So along the x-axis, we have to go negative L over 2. And along the z-axis, we go 0 to get from G to point B. All right, so we just take our 1/12 ml squared plus this ends up giving us 1/4 ml squared. And we'll see those so often that you'll learn and you'll get memorized. 1/12 plus 1/4 is 1/3. So that's 1/3 ml squared. So that's the inertia of a rod about its end. We'll see that all the time. What about the products of inertia? Do we need to worry about the products of inertia? Well, the rod still has two planes of symmetry about point B as well. And so we'll see that all of those go to 0. And indeed, if we look at this equation here, x is the only non-zero parameter, so every one of those will have a 0 in it. So all the products of inertia will stay 0. All right, so that's the parallel axis theorem. The other thing we can do with these equations is deal with a composite body. So let's say rather than this solid cylinder, we had a cylinder with inner radius r1, outer radius r2, right? We can subtract, so we could calculate that the IZZ for our hollow cylinder would just be IZZ for the outer minus IZZ for the inner. Let me just write out the answer, actually is easier here. So that would just be the inertia of the larger cylinder, 1/2 m r2 squared, minus the part that we removed, 1/2 m r1 squared. And notice that both of these are in the same coordinate system. The center of mass hasn't moved. If we move the center of mass, then things would get a little more complicated. The book has some additional examples if you want to see those. All right, so that's a composite body. Let's talk really quickly about principal axes. We hinted at this as we were looking at the pictures earlier. Okay, so what's a principal axis? Well, here we're going to have to use a little bit of linear algebra. But given any inertia matrix, given any inertia matrix for a body, we could define some properties of this inertia matrix. And we get them from knowing that the rotational kinetic energy of a body that has that inertia matrix would be given by 1/2 times the angular velocity vector transpose times I times the angular velocity vector. So this is the omega of the body that we've been finding throughout the class. Okay, so anyway, because of this property, we can prove a few things about the inertia matrix. The first one is that the inertia matrix has to be symmetric. The second comes from this and the fact that no omega can give us a negative number, right? A negative kinetic energy. The kinetic energy always has to be greater than 0. There's no way we can make this body spin so that it will have negative kinetic energy, right? So that tells us that I is positive definite. Because the definition of a positive definite matrix is that it's that for any vector x transpose AX is greater than 0. So because of these two properties, we can prove that there exists a rotation matrix R such that if we apply that to the system I prime, if we apply the rotation R transpose IR, we'll get an I prime that's diagonal. So our inertia matrix would just look like this: I11, 0, 0, I22, I33. So, so this one has no products of inertia. So, so in this case, we don't need to worry about products of inertia, and all we've done is apply a rotation, right? So, you know, whatever coordinate system we had started with, you know, maybe we've rotated it like this, right? Rotated it through some angle theta, and we could do that in 3 dimensions if needed, but we've just applied a rotation that's caused all of the products of inertia to vanish. So we can show then that that the products of inertia are really just an artifact of the coordinate system. They're a consequence of the choice of the coordinate system. If we could choose our axes correctly, if we could choose initially as we built the I matrix, if we could choose x prime, y prime, z prime as our axes, then we'd have a diagonal inertia matrix. All right, so all of that means that every body has a set of axes that that render the inertia matrix diagonal, and so we call those the principal axes, or they're the axes for which the inertia matrix is positive, or is diagonal, sorry. So if we went back to our example from a minute ago with this, oops. All right, if we went back to our example here of this cylinder, or of this right triangular prism, we saw that x, y, z are not principal axes, but after this rotation we should be able to get, we have 2 planes of symmetry, so we would get all the ixx, or all the products of inertia to vanish, and so these would be what we'd call the principal axes. All right, so products of inertia are nothing to be afraid of. They just mean that we have non-principal axes, right? That's all that they're trying to tell us, is that we've written our equations, we're doing things in a set of non-principal axes. All right, so the last thing we need to be able to use this to solve problems is to know how we're going to differentiate the angular momentum, because we said that the sum of the moments about point A was equal to the derivative of HA, right? Or plugging in, that's the derivative of the inertia matrix times omega. All right, so how do we differentiate this? Well, let's use our trick for the derivative of a vector. So if we attach a coordinate system x, y, z to the body, so the omega of the coordinate system is just equal to the omega of the body that we have right there, right? Then we can do the derivative in two parts. So that derivative, well, let's see, I guess I'll just write it this way for now. The derivative HA dot would just be, the inertia matrix is constant. Now we're taking the derivative of omega, keeping the axes fixed. I'm going to write this as partial with respect to time of omega. So this is with x, y, z fixed. All right, so we need that derivative of omega. And now we have the correction term, which is just omega of the coordinate system crossed into our original vector. So this tells us that this is the derivative of HA, but what about this term? This is funny to have the derivative of omega with x, y, z fixed, right? What do we do about that? Well, you'll recall that we talked earlier about the fact that the derivative of omega, of the angular velocity vector, that, if we were just taking the derivative of that, we'd again have the same thing. We'd have the derivative holding the unit vectors fixed, plus the correction term, omega cross omega. But this term has to be 0, right? Any vector crossed into itself is 0. So we saw earlier that the derivative in a fixed reference, with respect to the coordinate axes, is the same as the total derivative of omega. So that allows us to replace this term with the total derivative of omega, which we've usually called alpha in this class. So this equation boils down to what we have right here. And then that would be equal to the sum of the moments about point A. And that just shows that this here is a cross product right here. So to get angular, the sum of the moments, or get the derivative of angular momentum, we just have these two terms. We find the I alpha, and we find the omega cross I omega. And all of this was for XYZ attached to the body, right? But it's important to note that if we have XYZ attached to this body, or suppose we had a different coordinate system that was spinning relative to the body, right? If the body is axisymmetric and the coordinate system is spinning relative to the body, when we go to evaluate these inertia properties, right, we're going to have some x squareds plus, this would be some y squareds plus z squareds. Whether we evaluate these integrals in the xyz coordinate system or x prime, y prime, z prime that's spinning, all of the mass is going to have the same coordinates. There's always going to be a chunk of mass there. So those integrals are the same whether we use the body fixed or a coordinate system that the body is spinning about. So our XYZ coordinate system that we use for all of this is one, either body fixed, or two, an axis that the body is spinning about. And that's only true, that only works if the body is axisymmetric. So we can only use that second one in that case. All right, and now we have everything that we need to be able to solve the problem. We have our sum of the forces is equal to mass times acceleration. We can always use this equation, which says that the sum of the moments about the center of mass is the derivative of angular momentum about the center of mass. And we also have this second equation, and in a lot of cases we can neglect this term, so that we can also write the sum of the moments about some point A is derivative of angular momentum about point A. Notice the difference between these two, right? For one of these, for this one we're going to have inertia about point G. For this one we're going to have inertia about point A. So our solution strategy is to draw a free body diagram with all the forces acting on it, pick a body fixed coordinate system, and then we calculate omega and alpha, and we put them in the body fixed coordinate system here so that we can form hg and hg dot. Then we use these equations up here to write, we can write 6 equations for the sum of the forces and the sum, 3 for the sum of the forces, 3 for the sum of the moments. And if we're done, if everything works out, we're done, right? And the problem should always be determined by doing that. Usually we're not having to find all 6 of those components. All right, so that's our strategy. Let's go ahead and work an example problem. So here we're told we have a gyroscope that's spinning and precessing. It's spinning, so we have a constant spin about the axis of the gyroscope. I'm going to start a gyroscope up spinning so we can actually try this. So the gyroscope is spinning at a constant rate. It's held down here at this pin, and then it's observed to precess, or in other words, it's tilted at a constant angle of nutation, and it's precessing. So can you imagine that? If you've seen a top before, you've maybe seen something like that. Alright, I'll show you an example of this. Here I'm spinning up a gyroscope, and I'm giving it an angular velocity vector that will go this way. Okay, I think we've probably got enough momentum now. Now, here's my gyroscope, and I put it at a constant angle of nutation, and look what happens. It precesses at a constant rate. So the precession is the global motion it's going through, right? Let's try that again. Get back a little more. If I give it a smaller nutation angle, it's a little less wild. If I give it a little bigger nutation angle, it's going to precess more quickly. Right? So there's something interesting going on here. There's some connection between the spin rate of the gyroscope, the angle of nutation, and the precession, right, that causes the gyroscope to do this. And the dynamic equations are what keep it from falling down, that precession. So we'll go ahead and we will try to solve that problem. And we'll use the solution strategy that we just talked about to try to solve it. So let's go ahead and do that. So this is our gyroscope example. So I'll draw a 2D picture of the gyroscope because that will make things a little simpler for us. So suppose we have the gyroscope here, it's tilted, and the only thing that really matters in the gyroscope is this rotor. That's where all the mass is. All right, so there's that rotor. And we haven't said anything about the rotor. We'll worry about that in a minute. Okay, so anyway, we said that we have a constant angle of nutation. So the gyroscope is tilted over with theta being a constant. The gyroscope is spinning, and by the right-hand rule, we had a phi dot that was positive up. And we also saw that it was precessing. This was the slow motion. So the gyroscope was kind of moving into the page at any instant in time. All right, so let's go through and let's try to solve this. So step 1 was to draw a free body diagram. Put a lot of exclamation points. Everyone wants to skip that step. And if you're physicists, you probably don't believe in free body diagrams. You're just going to charge ahead, right? But let's draw a free body diagram. And let's neglect the mass of the frame. So the only mass that we have is the rotor. So we're going to have gravity pulling down on the rotor. And that's the only mass. And then we had my finger holding up the gyroscope. So there's some unknown reaction force in the vertical direction and some unknown reaction force in the horizontal direction there. Let's call this point A. This is the center of mass, point G. And so we should have everything that we need to describe the system. Okay, so step 1 was to draw a free body diagram. We're going to need some coordinate systems. So we're going to attach x, y, z to the gyro wheel, or to the rotor. Let's call it the rotor. And let's attach x prime, y prime, z prime to the frame. So what does that mean? That means that let's call this axis z. That's the axis of the rotor. And that axis will also always be z prime, which is of the frame. Let's call this axis y prime. And we'll put in parentheses here that at some instant in time, we could have y, this could be equal to y, only at some instant, right? Not for all time. All right, let's see, we're going to need some dimension. We need to know how far the rotor is from point A. And I think that's everything that we need to solve the problem. Let's also, let's call this the capital Z direction. So that's our fixed Z direction. Okay, so our purpose in doing all of this was to be able to define the inertia properties of the body. So let's start Well, let's start with them about G, I guess. Yeah, let's do everything about G in this problem. So anyway, so we can define the inertia properties using x, y, z. So IZZ, and let's just write this in terms of a radius of gyration. It's symmetric, so we're going to have that I, x, y, I, x, z, dot, 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 those are all going to be 0. So we can say IZZ is the mass times some radius of gyration, or some equivalent radius squared. And IXX, so x and y are in a plane of symmetry, or in the rotor in the symmetric plane. So IXX and IYY will be equal. We'll call those 1/2 m kp squared. So this is for the perpendicular direction, this is for the axial. By the way, Ka and Kp, which of these is greater? Axial or perpendicular? Pause the video and think about it. But I'll give you the answer now, Ka, because more of the mass is farther from the center, from the z-axis, than it is, right? If we look at the z-axis, we have more mass far from the center than if we look at the y-axis. So it's easier to spin the rotor about this axis. This would be like here, I, y, y. So it's easier to spin the rotor there. All right. They're the inertia properties, and notice that I, z prime, z prime is equal to I, z, z. The inertia is the same in that, in the x prime, y prime, z prime frame that's attached to the rotor. All right. So the next step in our solution strategy was to find omega and alpha. So let's go ahead and proceed with that. The angular velocity of our gyroscope, we have 2 rotations because theta is constant. So we'd have psi dot about the capital K, and we have phi dot about K prime, right? So now we've also said that phi dot was constant. Everything was happening before the rotor could decelerate very much. And we also know that psi dot was constant. So when we take the angular acceleration, we don't get anything from this first term. So the only term comes from phi dot times the omega of the coordinate system K prime crossed into K prime. So the x prime, y prime, z prime coordinate system is precessing only. So we have psi dot capital K, and capital K we can write as a cosine of theta in the K prime direction minus a sine theta in the J prime direction. Oops, sorry, those prime didn't show up at first. And then we're going to cross all of that in, oops, the K prime, primes keep vanishing. Cross all of that into K prime. So only the second term will survive. So alpha will be a negative phi dot psi dot sine theta. And then we also have to have j cross k, which is positive I, and that's what we have right there. There's our alpha. All right. Oops, that should be I prime. We could, okay, so then we can also write omega in the x prime, y prime, z prime. So that will be negative psi dot sine theta j prime plus phi dot minus, or no, phi dot plus psi dot cosine theta, all of that in the k prime. And these are the angular velocity and angular accelerations that we're going to need to plug in to get the angular momentum and derivative of angular momentum. We can check this really quick, and we should. We got that the angular acceleration was in the minus I. So by the right-hand rule, x prime is out of the page at point G. So this tells us that the angular acceleration is into the page. And if you imagine this gyroscope precessing with psi dot, the tip of the z prime vector here is going into the page, or in the negative I direction, or I prime direction. So everything seems to check out there. All right. So now we're ready to continue. The next step then will be to get the sum of the moments about the center of gravity is equal to hg dot. We could also do this at point A. So there we would take the sum of the moments about point A is equal to HA dot plus that correction term, MRG is seen from A cross AA, right? And actually this equation will work in our case because point A is a fixed point. We have things rotating about that, but it has zero acceleration. So that approach will probably be a little easier. If we use that approach, then we get the sum of the moments about point A. Sum of the moments about this point, we only have this term here. So sum of the moments about point A will give us a negative mg L sine theta in the I prime direction, right? We have a moment tipping over that way. And the sine is the correct angle because if the angle goes to 0, the moment goes to 0. So that checks out, though I got the moment by kind of looking at the geometry here. Okay, so the sum of the moments is negative mgl sine theta I prime. And that then has to be equal to the inertia matrix times alpha plus omega cross I omega. All right, so we're just about there. We want to transfer our inertia then to point A, and I'm going to use the prime coordinate system. So we can say that all of this will be equal to I about point A, x prime, I about point A, y prime, I about point A, z prime. There's no products of inertia, so this is diagonal. All of this times alpha. So this is alpha, the x prime component, alpha y prime component, alpha z prime component. We're putting these in the same coordinate system. So that's a really important point, right? These are in the same coordinate system. A lot of the work that we're doing is to put everything in appropriate coordinate systems. All right, plus that term right there. All right. So let's look just at the first term there. So the first term is negative mgl sine theta. That's the I component on the in the sum of the moments. And then that has to be equal to I x prime a alpha x prime plus whatever we get from this second term. All right, and let me just look. All right, and I guess we can also write this equation as omega crossed into HA, right? The angular momentum about point A. Because both of these have to be about point A. All right, so I'm just going to write this as omega cross HA and then dotted into the I direction. So we have a little bit of work to work that part out. Here we're practically done. Okay. So H sub A is just going to be the inertia matrix times omega, and way up above here we worked out the inertia. So so we can say H sub A, and we also worked out the omega. We had nothing in the I direction. So we had 0 in the I prime direction, and then we have a j prime component, so we have minus I y prime a times psi dot sine theta in the j prime direction, and then we have two terms in the k direction plus I z prime about point A. And there we had the phi dot plus psi dot cosine theta in the k prime direction. All right, and now if we want omega cross HA, then we're going to have the omega from up above crossed into all of this. So so we have a few different, so we're going to have a few different terms. Remember, the omega was just this part right here. Basically the same as what we wrote there. We could almost skip copying it, but let's do that to be complete. All right, so we'll have this, all of that crossed into what we have up above there. And so notice in the everything here is going to end up in the I direction. We're going to have some j cross k's and some k cross j's. All right, so I'm going to spare you all of the math and just give you the answer here. Omega cross HA. It's going to be all in the I direction, and it's going to end up being I y prime a minus I z prime a, all of that times psi dot sine theta times psi dot cosine theta plus phi dot. And again, it's all in this I prime direction. And So if we plug that in up here, we get minus mgl sine theta is equal to I x prime a times alpha x, which we had was the negative product of the rates, negative phi dot psi dot sine theta, and that's in the I prime direction, plus this term up here, right? And so we get a big mess of terms, but let's notice a few things. I guess we'll have to do just a tiny bit more simplification to make sense of this. Let's plug in for the various inertias, I guess. So negative mgl sine theta. The inertia about the x-axis. X was a perpendicular axis, remember? Right? And when we transfer x from G to point A, there's no change. Well, let's see. No, there's actually going to be a translation term there, because we're transferring down a length L. Z is the only one that will have no parallel axis term. Okay, so anyway, so this will be equal to, I'll move that negative to the outside, m kappa perpendicular squared plus m times the L squared that we're transferring that, times phi dot psi dot sine theta. And then here, Iyy will be the same as Izz, so that will also be mkp squared plus ml squared. And then we're going to subtract from that the axial inertia, so mka squared. And then we have this product of terms again. All right, and here's our answer. And everything manages to balance out. I guess we'll just mention quickly, if we have the spin rate phi dot being much greater than psi dot, that's what was kind of going on with our gyroscope, then the term that's really going to dominate is this term right here. And notice the signs on these terms match. So what's really happening is this is the moment due to gravity. And that's being countered by the by the derivative of angular momentum, HA dot. The whole thing on the right is actually HA dot, but that's the dominant term. They both have the same sign, so basically this tells us that the gyroscope doesn't fall over because these moments balance. In other words, this would be like a moment. This would be the sum of the moments about point A. It's in the negative x direction. And that's being balanced by HA dot, right, which is also in that negative direction. Another way you could think of this is you could kind of move this to the other side, and you could say, well, gravity is applying a moment this way, but then HA dot is like an inertial moment that's trying to cancel it, so that's trying to tip the gyroscope back up, and these two cancel so the gyroscope doesn't fall over.